In the third module of the last lecture, we started to discuss the position kinematics problem for a 4-bar mechanism. In this module, we will continue this discussion further. Recall that the position kinematics problem for a 4-bar mechanism is stated as follows. Given the angle θ2, find the angles θ3 and θ4. Here, without loss of generality, we assume that the link 2 is the driven link. In other words, we know the angle θ2. Furthermore, the link lengths A, B, C, D are assumed to be given. The angles θ2, θ3 and θ4 are defined as shown in the picture here. θ2 is the angle made by the vector O2A with the x-axis of the global coordinate system. θ3 is the angle made by the vector AB with the x-axis of a local non-rotating coordinate system that is attached to the pivot A. So essentially θ3 is the angle made by the vector AB with the x-axis of the global coordinate system, and θ4 is the angle made by the vector O4B with the x-axis of the global coordinate system. All these angles are measured at the tail or root of the vectors. Now, using the complex number representation of vectors and vector loop closure equations, we showed that the solutions to θ3 and θ4 can be obtained by solving two trigonometric equations of the form shown here. Note here that the only two unknowns here are θ3 and θ4. A, B, C, D are link lengths that are already known because we have synthesized the mechanism. θ2, as I stated earlier, is assumed to be known. θ1 is the angle that the fixed link makes with the global coordinate system, and so it is a constant. Usually it is 0. So these two equations are of the standard form of problem 2 that we discussed previously, and we know how to solve them, and we have seen that in general there are two solutions for θ3 and θ4. So what we want to understand first is the geometric meaning of these two solutions θ3 and θ4. Then we will look at an example that illustrates the use of these equations that we have derived for solving the position kinematics of a 4-bar mechanism. A typical picture for depicting the two solutions of the 4-bar mechanism is shown here. The two angles of θ3 are marked as θ3 and θ3 prime, and the corresponding angles for θ4 are marked as θ4 and θ4 prime in this picture. In our previous presentation, we understood that there may be at most two solutions to the equations that we are solving, because at the end of the day, we were solving a quadratic equation. Now, we will see geometrically why there can be at most two solutions. So suppose θ2 is known. θ2 is known or fixed means the position vector of point A is fixed. Now when point A is fixed, then the point B or the pivot B can only lie on a circle that is centered at A and with radius B. Similarly, since O4 is fixed, the point B can also lie only on a circle with center at O4 and radius C, the length of the link O4B. Now two circles can intersect at most 2 points, which is shown as B and B prime in this picture. So there can be at most two solutions. Now one thing you should note is that depending on the link lengths and the angle θ2, there may be no solution at all. What does it physically mean to have no solution? That means that either the mechanism cannot be assembled at all given the link lengths, or the input angle cannot take that particular value of θ2 that we have prescribed. It is also possible that the two circles just touch each other and they don't intersect. If the two circles touch each other, it means that AB and BO4 are collinear. In other words, the coupler and the output link are collinear. This is called a stationary configuration or toggle configuration of the 4-bar mechanism, and we will talk about it in much detail later on. There is a common terminology used to describe the two solutions of the 4-bar mechanism. So a 4-bar mechanism is said to be either in the open configuration or in the crossed configuration. Open means that if you restrict the angle theta 2 to be between 0 and pi by 2, then the links adjacent to the driving link or O2A, in this case AB and O2O4, they do not intersect. And crossed means that they intersect. To go from an open configuration to a crossed configuration, you have to disassemble the mechanism at the pivot B and then reassemble it again. And whether a mechanism will be in the open configuration or the crossed configuration depends on how it is assembled. It is not evident from the link lengths alone. Now let us go through an example. Consider a 4-bar mechanism with link lengths 40 mm, 120 mm, 80 mm and 100 mm. Recall the notation. D is my fixed link, A is my input link, B is my coupler, and C is the length of the output link. The angle theta 1 is 0 degree, the angle theta 2 is 40 degree, and we have to find all possible values of theta 3 and theta 4. As we said, to compute theta 3 and theta 4, we have to solve two equations of this form here, and A, B, C1, C2 are dependent only on the link lengths and the angle theta 2 and theta 1, which are known. A is equal to B equal to 0.12 meters, B equal to minus C is minus 0.08 meter, C1 and C2 we can obtain from the expressions given here. So in fact, from the problem data, we know all the constants A, B, C1 and C2. Then we have seen that we can eliminate one of the variables, for example theta 3, and we obtain an equation of the form P sine theta 4 plus Q cos theta 4 plus R equal to 0, where P, Q and R are defined in terms of A, B, C1 and C2. Substituting A, B, C1 and C2 from the previous slide and going through the calculation, the values you obtain are shown on the slide. Then we know that one way of solving the problem 2 is to convert the trigonometric equation into a polynomial equation of the form sx squared plus tx plus u equal to 0, where s, t and u are functions of p, q and r, and x is tan theta over 2. Using that, we had the formula for theta 4.1 and theta 4.2 in terms of a tan 2 function, and s, t and u are defined here, and their numerical values can be computed because we have already computed p, q and r. So the two angles that we get for theta 4 are theta 4.1 as 262 degrees and theta 4.2 as 57.32 degrees. Once we have obtained theta 4.1 and theta 4.2, we can obtain the two corresponding angles theta 3.1 and theta 3.2. Again, note that the equations that I had were A cos theta 3 plus B cos theta 4 plus C1 equal to 0, and A sine theta 3 plus B sine theta 4 plus C2 equal to 0. So once I have solved for theta 4, the only unknown here is theta 3. And again, I can use the a tan 2 function to solve for theta 3. And the expressions are shown here. And if you use these to solve for theta 3.1 and theta 3.2, we get the following angles. So in this case, there are indeed two solutions to the position kinematics problem. So how do these two solutions look like geometrically? What is the sketch of the two solutions? These two solutions will look as depicted in the picture here, where this is A, this is B, this is B prime, this is O2, O4. this angle is theta 32, this angle is theta 42, this angle is theta 31, and this angle is theta 41. In the last lecture, I claimed that once you know the angles theta 2, theta 3, and theta 4, you can compute the position of any point on any link of the mechanism. These three angles completely describe the mechanism. We will now see how we can do this. First, let us consider 2 points on the input link and output link respectively. So S is a point on the input link and U is a point on the output link. So let's look at the point U on the output link. This point will be specified or will be known in a locally rotating coordinate system of the link O4UB. This local rotating coordinate system is shown in blue here. We know the length U and the angle delta 4. What you have to determine is the position vector of the point U in the global reference frame or the global coordinate system, marked with the capital X, capital Y axis here, and with the origin at O2. Similarly, for the point S, the locally rotating coordinate system is assumed to be here, and the angle delta 2 and the length S unknown. We have to find the position of point S in the global coordinate system or the global reference frame. So let's look at the point S first. We are calling RS as the position vector of point S. So RS is the same as O2S. The length of O2S is small s, and the angle that O2S makes with the x-axis of the global coordinate system is theta 2 plus delta 2. So this is equal to S e to the power of j theta 2 plus delta 2. And that's what is written here. Now let's look at the position vector of the point U, which we denote by RU here. So RU is the vector O2U. RU equals to O2U is equals to O2O4 plus O4U. And all these vectors have to be expressed in the global coordinate system or the GCS. Now O2O4, which is also denoted as RO4, is equal to D e to the power of j theta 1. And recall, this was my length D, which was my fixed link. This was A, which was my driven link. B was my coupler, and C was my output link length. Now the vector O4U is U e to the power of j theta 4 plus delta 4, which we have shown here or written here. So what do we mean by computing position of any points on the links? We mean that if there is a local coordinate frame or LRCS in which a point is known on a given link, then we can determine the position of that point in the global coordinate system, given we know the angles theta 2, theta 3, and theta 4. And we just showed it for the input link and the output link. Now let us look at the coupler. P is a point on the coupler. Again, the locally rotating coordinate system is shown in blue here, and we know the length of the vector AP and the angle delta 3 that the vector AP makes with the x-axis of the LRCS. The position vector of the point P, which is RP, or also the vector O2P. So RP equals to O2P is equal to O2A plus AP. So this is written as RA. So O2A is the same as RA and AP is the same as RPA. Now O2A or RA is A e to the power of j theta 2 and AP is P e to the power of j theta 3 plus delta 3. P is the length of the vector and theta 3 plus delta 3 is the angle made by the vector AP with the x-axis of LNCS or locally non-rotating coordinate system, which is the same as the angle made with the x-axis of the global coordinate system. So if I expand A e to the power of j theta 2 and P e to the power of j theta 3 plus delta 3 using Euler's formula, I get these two expressions. And if I add these two, I will get the position vector of point P. Note everything on the right hand side. So A, theta 2, P, theta 3, delta 3 are all known. So you can just evaluate these expressions and do the addition and you will get the answer. There is a j missing here, so this should be plus j sine theta 3 plus delta 3. Those of you who have looked at the textbook, you may have noticed that the way we solved the position kinematics problem for finding theta 3 and theta 4 looked a bit different from the textbook. The way I presented the 4-bar solution is to first introduce solutions of some general trigonometric equations and then show that the 4-bar equations are an instance of this general form. Alternatively, we could have directly tried to solve the two scalar equations from the vector loop closure equations. And these two scalar equations that we had derived earlier are shown here. Then in the process of the derivation, we would arrive at an equation which is very useful for analytical synthesis. And it is known in the literature as Freudenstein's equations. So for completeness, I will show you how we can arrive at Freudenstein's equations. First note that theta 1 equal to 0 is a choice that we can make. So if I substitute theta 1 equal to 0 in these equations, I get cos theta 1 as 1. So this term just becomes d, and sine theta 1 as 0. So this term goes away from the equations. So in the second equation, there is no sine theta 1 term. Again, note that these are two equations in two variables, theta 3 and theta 4. So the process that I will do is same as I had done before. I will try to eliminate one variable. So what I first do is get the expression of b cos theta 3 from the first equation and get the expression of b sine theta 3 from the second equation. Then I will square and add to eliminate theta 3 because cos square theta 3 plus sine square theta 3 equals to 1. So if I square and add, the left hand side becomes b square and the right hand side is shown here. So this is the expression from the previous slide. Now I will expand the squares, simplify and collect terms. So I am skipping 2 or 3 steps of algebra here. But the essential thing that you need to do is expand the squares and use the fact cos square theta plus sine square theta equals to 1. Note here that the only variable is theta 4. So now we can rearrange this equation a little bit. First, what we do is divide throughout by this term 2ac and then we rearrange some terms. So if we do this, we form an equation of the following form where the constants k1, k2 and k3 are defined here. And then noting that this right hand side is nothing but cos of theta 2 minus theta 4, we get the following equation. This equation is known as Freudenstein's equation and it is used in analytical design. So you may be wondering that why did we do the derivation for the position kinematic solutions of the 4-bar mechanism in the way we did. The reason is that that structure or those two problems that I mentioned, they are very important and can arise over and over again when you try to solve position kinematics of simple closed loop chains. So I should add the word simple here. What does a simple closed loop chain mean? A simple closed loop chain means that there is only one loop. So I can have many links, but I just have one single loop. I cannot have the ground link as a ternary link. The ground link is only a binary link, and all other links are binary links. As I said, solving the direct position kinematics of all planar simple closed loop chains made up of binary links and revolute joints can be reduced to solving two equations of the form shown in problem 2. And this is for any number of links, n equal to 5, 10, 100, whatever be the number. So let's just get an intuition for this, why this should be true. And the details of this I will show in another module. First note that a simple closed loop mechanism of n links, where n can be any number, I'm not specifying it here, but you can show that the simple closed loop mechanism of n links has degree of freedom n minus 3. And if there are n links, then you will need n minus 1 joint angles to define the configuration of the mechanism. So first make sure that this claim makes sense. If you put n equal to 4, which is the 4-bar mechanism you know, then you get 4 minus 3 as 1, which you know is true. 4-bar mechanism has 1 degree of freedom. And you need 4 minus 1 or 3 joint angles to define the configuration of the mechanism. And you just saw that it is true. If we know the 3 angles, theta 2, theta 3, and theta 4, we can know any point on the mechanism in the global coordinate system. Therefore, there will always be 2 unknown angles, n minus 1 minus n minus 3. You have to compute these 2 unknown angles by solving equations of the form given by problem 2. We just saw the case of n equal to 4. In the homework, we will see the case of n equal to 5.